Salt insulation includes the isolation of airborne salt, solid salt, or impact salt. Airborne salt isolation refers to isolating the salt energy of the external space salt field with an enclosure structure. Solid salt isolation means that the enclosure structure isolates the salt energy radiated from the impact energy into the building space. Solid salt isolation is different from vibration isolation. Solid salt is to isolate the air salt reaching the receiver, while vibration isolation is to isolate the solid vibration felt by the receiver. The transmission coefficient refers to the ratio of the acoustic energy transmitted through the component to the incident acoustic energy, which is always less than 1. The salt insulation represents the insulation ability of the component to air salt and is always greater than 0. Knowing the amount of salt insulation, the transmission coefficient can be calculated inversely. The larger the tau, the smaller the r, and the worse the salt insulation performance of the component. The same structure has different salt insulation for incident salt views of different frequencies. The salt insulation of components need to be measured in a standard salt insulation laboratory, taking into account the frequency characteristics of human hearing and the salt insulation frequency characteristics of general components. The single value evaluation index, weighted salt insulation, is used to evaluate the salt insulation performance of components. In order to reflect the difference in salt insulation effect caused by the spectral characteristics of the salt source, two spectral corrections C and CTR are introduced. The application scope of C is a facility that mainly radiates medium and high frequency noise, and the application scope of CTR is a facility that mainly radiates medium and low frequency noise. This is a one-third active airborne salt insulation reference graph and the salt pressure level spectrogram for calculating the spectral correction amount. Use the reference curve with the salt insulation measurement curve to find the RW value, find the LIZ value on the salt pressure level spectrogram, and substitute the measured value RW and LIZ into the above spectrum correction calculation formula to obtain CZ, according to the sum of RW and CZ, to check the building salt insulation evaluation standard. The air salt insulation performance grade can be obtained, which is divided into 9 grades. Plot the measured amount of air salt insulation in the one-third active band, accurate to 0.1 decibel, as a frequency characteristic curve of salt insulation in Figure A, and plot the one-third active air salt insulation reference curve in Figure B with the same coordinate scale overlay on Figure A as shown in Figure C. The abscissors are overlapped, and the 0 decibel ordinate of the frequency curve is aligned with a certain integer ordinate of the frequency characteristic curve of salt insulation. Move the reference curve 1 decibel per step until the sum of the low values of the salt insulation frequency characteristic curve in the same frequency band. Then the reference curve is as large as possible, but not more than 32 decibel. At this time, the integer decibel of the ordinate on the frequency characteristic curve of the salt insulation amount corresponding to the 0 decibel line on the reference curve is a single value evaluation value corresponding to this group of measurement quantities, and its abscissor is 500 Hz. It can be seen from Figure CZ corresponding to 100, 125, 160, 200, 250, 315, and 400 Hz. The values of the salt insulation frequency characteristic curve lower than the reference curve are 4, 5, 6, 6, 5, 2, 3, and the sum is 31 decibel. At this time, the intersection point of the two curves is the intersection point of the reference curve 0 dB and 500 Hz. The value of the ordinate of the intersection point on the sound insulation frequency characteristic curve is 47 dB. That is, Rw is 47 dB. This is a typical sound insulation frequency characteristic curve of a single-layer homogeneous compact wall. It can be seen from the figure that the low-frequency sound insulation is controlled by the stiffness, and the sound insulation decreases with the increase of the frequency. The stiffness refers to the ability of the component to resist elastic displacement. As the frequency increases, the mass effect increases. At some frequencies, the stiffness and mass effect cancel each other out, resulting in resonance. F0 is the fundamental frequency of resonance, and the sound insulation reaches a minimum value, which starts to be controlled by damping. This damping refers to internal damping, which refers to the energy loss caused by friction between particles inside the medium. At this time, the reduction of the sound insulation mainly depends on the damping of the components, and the smaller the damping is, the lower the sound insulation is. When the frequency continues to increase, the quality begins to play a major controlling role, and the sound insulation increases with the frequency. At Fc, the sound insulation is greatly reduced, forming a valley of sound insulation called the matching valley. Fc is called the coincidence critical frequency. Since the resonant frequency is very low, around 5 to 20 Hz, it can be considered that the sound insulation in the main audio frequency range is controlled by quality, and the effects of stiffness and damping can be ignored. Treat the wall as are stiffened and are dampened, and ignore the wall's boundary conditions, assuming that the wall is infinite. Then the calculation formula of the sound insulation amount when the sound wave is perpendicular to the wall can be obtained. In general, the product of pi and the mass per unit area of the wall and the frequency of the incident sound is much smaller than the medium characteristic impedance of air, so the formula for sound insulation can be simplified. When the sound waves are randomly incident, the sound insulation of the wall is about 5 dB lower than that of the normal incidence. It can be seen from this formula that the greater the mass per unit area of the wall, the better the sound insulation effect. Every time the mass per unit area doubles, the sound insulation increases by 6 dB, which is the law of mass. Only 4 to 5 dB can actually be used. At the same time, it can be seen that each time the incident sound frequency doubles, the sound insulation also increases by 6 dB, which can only reach 3 to 5 dB in practice. This graph is a mass law straight line drawn according to this formula. The abscissor is a logarithmic scale, and the ordinate is a linear scale. It can be seen from the figure that the matching value is also seen, and the higher the quality of the material, the higher the matching critical frequency. The actual single-layer homogeneous compact wall is an elastic plate with a certain stiffness, which will produce forced bending vibration under the excitation of a obliquely incident acoustic wave, and the bending wave propagates along the plate surface. When the propagation speed of the bending wave is equal to the propagation speed of the free bending wave inherent in the plate bends with the incident wave so that a large amount of incident sound energy is transmitted to the other side, which is called the coincidence effect. The coincidence critical frequency is the lowest frequency at which the coincidence effect occurs, which occurs at grazing incidence, or when the angle of incidence is equal to 90 degrees. Under normal incidence, the plate will not have bending vibration, only longitudinal vibration in the same direction as the sound wave propagation. Upon diffuse incidence, a coincident value is formed at Fc. The depth of the meshing valley is related to the internal loss factor of the material. The smaller the internal loss factor, the deeper the meshing valley. Applying damping material can make the meshing valley shallow. The meshing valley should be avoided to fall within 100 to 2500 Hz. It can be seen from the figure that the meshing critical frequency with sink hard and solid walls is low, and the meshing critical frequency with thin and elastic walls is high. According to the law of mass, it is uneconomical to increase the salt insulation by increasing the thickness of the wall, and it is also unreasonable to increase the self-weight of the structure. The double wall can use the airspace to improve the salt insulation without increasing the material and quality. The airspace is equivalent to a spring connecting two walls, and the vibration is damped by the elastic deformation of the airspace. The salt insulation of a double wall is equal to the salt insulation of two single walls plus the salt insulation of an airspace. It can be seen from the figure that the additional salt insulation of the air interlayer is related to the thickness of the air interlayer, with increase with the increase of the thickness of the air interlayer, but does not increase after 10 cm. The solid line represents the additional salt insulation when the two sides of the double wall are completely separated, and the maximum additional salt insulation can reach 12 dB. The dotted line represents the additional salt insulation when there is a raised connection between the walls on both sides. That is a salt bridge. Compared with the solid line, the maximum additional salt insulation is reduced by 4 dB. The airspace and the double wall form a vibrating system. When the frequency of the incident salt wave is the same as the natural frequency of the vibrating system, resonance occurs, resulting in a significant increase in the transmission of acoustic energy. Therefore, F should be made larger than the product of F0 and the square root of 2. The dashed line in the figure represents the salt insulation of a single layer wall equal to the total weight of the double layer wall. The solid line of segment AB and the dashed line coincide, and F is less than F0, indicating that the double layer wall vibrates as a wall. This is similar to the single layer wall of the same weight. The solid line in segment BC is below the dotted line with the first drop in salt insulation. The double layer wall resonates at the fundamental frequency, and the salt insulation is larger than that of a single layer wall of the same weight. The solid line in the DEF segment is above the dotted line. F is greater than the product of F0 and the square root of 2, and the salt insulation of a double layer wall is greater than that of a single layer wall of the same weight. Harmonic resonance occurs at the harmonic frequency of F0, forming a series of coincident valleys. This is a formula for calculating the natural frequency of a double wall. In order to make the natural frequency not fall within the main audio frequency range, porous material can be filled in the air interlayer, and the walls on both sides are made of different materials on thickness, so that the natural frequency is less than 70 Hz, so as to ensure that the frequency range above 100 Hz has enough salt insulation. According to the law of quality, the salt insulation performance of light building materials is very poor, and it is necessary to take measures to improve its salt insulation effect. The main measures to improve the salt insulation effect of lightweight walls are: 1. Multi-layer composite, filled with porous materials. That is, the multi-layer dense plates are separated by porous materials to form a sandwich structure. 2. Double wall separation. That is, to make a separate double wall. 3. Elastic connection. That is, elastic cushion is used between the plate and the keel. 4. The thin plates are stacked, and the staggered shapes are stacked. That is to say, double layer or multi-layer shapes are staggered and superimposed, so that The critical frequency of the mass is roomed up beyond the main audio frequency range. 5. The wall panels are made of different thicknesses of materials to avoid matching the critical frequency falling within the range of 100 to 2500 Hz. 6. Increased structural damping. The sound insulation capacity of doors and windows is much larger than that of walls, with a weak link of sound insulation. For door-leaf heavy materials or multi-layer composite structures can be used, with double doors, enclosed entry posts, and sound lock. For windows, thickened glass, double layer, and multi-layer glass can be used. The glass is of different thickness, and the layers are not arranged in parallel. The window frames between the glass are arranged with sound-absorbing materials. For door and window gaps, it is required to meet processing accuracy, strength and durability requirements, reduce or seal gaps, and avoid straight-through seams. Think about it. What sound insulation measures are there in terms of architectural planning and space layout? From the perspective of NJCV, the machine room of the air conditioning system is generally arranged close to the room, and many are arranged indoors. How to isolate the sound?